Hello friends, welcome to Susan and John MathTube. Today we are going to continue our discussion about the probability distribution function, special distributions. In the last video, we learned about binomial distribution, and today in this video we are going to discuss about Poisson distribution. Okay, let's start. And I hope you're ready with a pen and a piece of paper. So remember, the first condition is events should occur independently. And the second condition, the probability that an event occurs in a given space or time does not change. And remember, this space or time refers to length, area, volume. And the next one, lambda means average rate of occurrence with respect to space or time. So let's imagine a straight road, and for convenience sake, let's say 20 kilometers straight road, and in an average there will be 2 buildings per kilometer. So I told you, in an average there will be 2 buildings in a kilometer. So let's say this is 1 kilometer, this is another one, this is another one, it goes like this. Now remember, the buildings can be anywhere here. So that is actually our events. It's kind of like the events which occur independently. But there will be an average of 2 buildings. Maybe in the first 1 kilometer you see the buildings here. In the next it might be here. In the next it might be here and here. And remember, we are able to predict, or we are able to say the average rate per time or per space. And remember, this space refers to length, area and volume. Okay, now as usual I'm going for the discrete random variable, and I'm going to associate with the number of times the event occurs per space or per time. And this is the notation. Like in the last video we saw the symbol for binomial is small b. Here I'm using P naught for Poisson, and this is the formula. And I want you to note these two things. Anyway, to understand clearly, let's go for an example. So look at this. A particular YouTube channel receives 300 views per hour in an average. So find the probability of getting 10 views in a given minute. And the second one, less than 3 views in a given minute. And the third one, 15 views in 2 minutes. Okay, so I have the question over here. Now look at this. We know that in an average the channel receives 300 views per hour. So here things are defined in terms of time, not in terms of space, not in terms of length or area or volume, but in terms of time. And the average value is given per hour. But look at this, they are asking you the probability values in minute, and in the last part it's in 2 minutes. So the first thing you have to do is you have to convert the given average value into minutes. So the average views per hour, that is 300. That means in 60 minutes, you know that 1 hour means 60 minutes, we get 300 views. That is, I'm going to divide by 60 so that it will become 1 minute. That is, in 1 minute there will be 5 views. Okay, that's it. So I know the average value per minute. Now I'll be able to solve the first and the second question with the help of Poisson's distribution. So let's define the random variable as a number of views per minute, and clearly capital X follows Poisson distribution, and I hope you remember this character from the last video. X number of success, the required number of success, and lambda equal to 5. Okay, so this is the formula. Now that's it. Just plug in the lambda value and we have the probability distribution function for X number of success. So read the first question. What is the probability of getting 10 views? So we are expecting 10 success in a given minute. We already converted this average into minute, so now you don't have to worry about this part. So the required probability is the number of views is equal to 10. Look at this. We define capital X to be associated with the number of views or the average number of views, and that will be, you just plug in 10 here and use a calculator. Now the second part. So find the probability of getting less than 3 views in a given minute. I have already converted the system into minute, and to be exact into 1 minute. So we are worried about the first part. And remember, capital X stands for the number of views. So we want capital X to be less than 3. Yeah, there it goes. This is the probability. And less than 3 means it can be 0, 1, 2. And you know what to do next. You have to add them up. Now, to find X equal to 0, you have to plug in 0 here. I put that red color over here. And then for X equal to 1, you have to plug in 1. And same thing, substitute, use a calculator and simplify. That's approximately 12%. Okay, now for the second part, it was in 1 minute, and even the first part, it was in 1 minute. But the last part is in 2 minutes. So I'm going to redefine, and if you want, you can use capital X. I'm going for another variable y. So let y be the discrete random variable associated with the average number of views per 2 minutes. So look at this, it's per 2 minutes. You can guess that. And let's say y follows Poisson distribution with parameter lambda dash. Lambda dash means the average number of views per 2 minutes. In a minute it was 5. So definitely the average in 2 minutes will be, guess please. Yeah, that will be equal to 10. I'll repeat. In 1 minute it was 5 views. So we expect in 2 minutes it's to be 10. And never forget, average stands for expectation. And so we have this formula, and I'm going to substitute the value of lambda dash, and that makes it 10 to the power y. Okay, that's it. Now we are ready for the last part. So remember, y stands for the number of views per 2 minutes. So the last probability is probability of capital Y is equal to 15. And that's it. Now plug in the values, use a calculator and check. Okay, now let's go for one more question. And this is from your past paper. So the first part is define Poisson distribution. A survey report shows that The probability is 0.001 that a car will have a flat tire while driving over a certain bridge. What is the probability that among 2000 cars driven over this bridge, the first part, not more than 1 will have a flat tire, the second part, more than 3 will have a flat tire, and the third part, exactly 4 will have a flat tire. Okay, now let's start. So look at this. A car which will pass through that bridge. We have two options. We can look at this question once more. So the car will either have a flat tire or it will not have a flat tire. And that means it's a clear case of binomial, not Poisson. This is a clear case of binomial because when you look at a car, according to this experiment, it may have a flat tire once it crosses the bridge, or it may not have a flat tire. So clearly it's binomial. But look at this. The probability of success is very, very, very small. So you remember something called Poisson approximation for binomial. That means you can convert binomial problems into Poisson if the probability of success is very small and n is large enough. So look at this. We have a car which crosses the bridge and it can have a flat tire or not have a flat tire. And it's being repeated again and again and again, to be exact 2000 times. And that means it's a clear case of binomial distribution. Now look at this. The probability is very small. So I suspect that Poisson approximation to our binomial can be applied. And let's check. I'll give you a rough rule to check. It doesn't work everywhere, but this is one of the best rough rules. So the first thing you have to find is n into p. You multiply n and p and check whether it is less than 5 or not. Of course, it's less than 5. Now what you do is you check whether n is greater than 50 or not. Yeah, both the conditions are satisfied. Some books don't go for the second condition, they go for only the first condition. The first condition is said to be a strong condition. Anyway, this means our binomial problem can be changed into Poisson. And when we change into Poisson, we always want lambda, the average rate. This average rate is given by lambda is equal to np, and np is nothing but 2. So here we have lambda equal to 2, and let's define the random variable. Let capital X be associated with the number of cars having flat tire. So capital X follows Poisson distribution with lambda equal to 2. And now the formula, e power minus lambda, lambda to the power x by x factorial, and we know the value of lambda, just plug in that value and we have the formula. Okay, so the first part, if you want you can rewind and check it. Otherwise I have the question over here. Not more than 1 will have flat tire. Look at this, we define capital X to be the number of cars with flat tire. So the required probability will be probability capital X less than or equal to 1. It's given not more than 1. And less than or equal to 1 means it can be 0 or 1. Then add them up. And now what you do is you plug in the value over here. You can put x equal to 0, and for the second one you can put x equal to 1. And that's it. Simplify, use the calculator. Yeah, it's approximately 40%. And now let's go for the second part. More than 3 will have a flat tire. And remember, capital X stands for the number of cars having flat tires. So the required probability will be greater than 3. But greater than 3 means it can be from 4, 5, 6 up to 2000. And practically we will not be able to add all those probabilities. So what we do is we just use the property which we learned in discrete PDF. That is 1 minus x less than or equal to 3. And that means 0, 1, 2, 3, and let's add them up. You already know the value from the first part. So plug in, and that's 14%. So that's very low. And now let's go for the third part. Exactly 4 will have a flat tire. So the required probability is x equal to 4. Plug in that value, and that's it. So just now we learned how to convert a few binomial problems into Poisson, and we suspect that the binomial can be changed into Poisson if the probability of success is very small and n is large enough. And I gave you the rough rule: n into p must be less than 5 and n must be greater than 50. However, some books tends to go for the first condition, not for the second condition. Anyway, let's check out one more question. There is a lab experiment, and the average number of radioactive particles. Look at this. The average number is given. That means we are going for Poisson distribution. And it's also given in terms of time. So the average value is 4. That means lambda equal to 4. So what is the probability? There will be 6 particles in a given millisecond. Okay, let's start. Let's define the random variable capital X, and then lambda equal to 4, and then we write the notation and the distribution, and that's it. We are ready for the probability. So what is the probability? 6 particles. So look at this. We define capital X to be the required number of particles. So it will be equal to 6, and plug in that 6. That's it, 10%. Okay, now let's go for one more question, and I found it very repetitive. I saw it in many of your past papers. So let's start. So in a factory which produces lens, there's a very small chance. Yeah, I think this is a binomial problem which we can change into Poisson. The word small probability. The lenses are, now it's a little bit depressing because this n is 10. Earlier I told you n should be greater than 50. But I told you one more thing. Many books seem to reject the second condition. And well, let's try. So what's the probability? The packet will contain no defective lens, at least one defective lens, and at most 2 defective lens. So as I told you, the lens can be defective or not defective. So clearly it's binomial. It's repeated 10 times because the packets are of size 10. Now if you're planning to use binomial, you can of course use binomial. You don't have to approximate into Poisson. Yes, if you have a powerful calculator, you can do it easily with binomial. Okay, so this is what you're supposed to use. N equal to 10 and P equal to 1 by 1500. Okay, now I want you to calculate this by yourself, and you can comment the answers in the comment section. Okay, now if you look at the probability, it's very small and it's actually less than 2, that n into p. But the second condition gets violated. Anyhow, I want you to try it with Poisson. So this is what you are going to use. So use both methods, compare the values, check whether you're satisfied with the answer you get from the Poisson approximation. And anyway, write both the answers in the comment box. So that's it, my friends. I'll be back with another video in which we will discuss about hypergeometric distribution. And till then, bye.